All right, so our third lecture for session 14 of the Data Science Fellowship Program is on supervised learning. So I will go into the details of supervised learning now. All right, staying with the theme that we have had all day long. And if you haven't, click on the links in the lecture slides. It's actually quite useful, I think, to look at the 1,000 most common words, but using the 1,000 most common words in the English language, I would describe supervised learning as building an information map to name different groups. Okay. And more technically, as we've discussed previously, in supervised learning, we want to use algorithms that will construct a map between features and the target class. Right? This is what the machine learning is doing. It's basically devising these rules, right? Or the map to connect the two. The reason we want to develop this map in the first place is to model unclassified sources and ultimately predict their classification, or if we're dealing with a regression problem, try to estimate their temperature, mass, etc. Okay. Hopefully, we are able to do all of this with a high degree of accuracy and also very small uncertainties on whatever it is that we're predicting with our algorithms. Okay. So here is my sort of single go-to slide summary of all of supervised learning. Okay, so we start, right? The process itself starts with labeled data. So this means a subset of the data where we have estimates of the features. We've measured all of the features of the data, and we also know their labels. Now, it is critical, it is extremely critical that this labeled data is then split into what is then called a training set and a test set. And this is something we were not doing in the first notebook that we worked on today. I'll explain why this is important though. The training data is then passed into the machine learning model. And the machine learning model, using the features and the labels for the training data, develops the map, develops the rules for how you go from inputs to outputs in order to basically build the model. Now, this split of the labeled data into the test data is how we can control against overfitting. Because once we've learned the rules from the training data, we can pass the test data into the machine learning model, and we can get predictions for the test data based on the rules learned for the training data, and we can compare those predictions to the actual correct answers, to the labels of the test data. So in this way, we're able to evaluate how well the model works on independent data. Now, why is this critically important? As we learn about more and more in different machine learning algorithms, they will in many ways become more and more complex and more abstract. In fact, in this diagram, the machine learning model is very intentionally shown as a black box. And that's because it is very difficult, and I would even contend in the vast majority of cases, it is impossible to actually understand why a machine learning model has made the decision that it has made. Okay, these things are basically black boxes. But that means that it's possible, right, as you tune your model, as you adjust parameters, to create a model that can perfectly replicate what is present in the training data, right? But that may not generalize well. You may not be able to make predictions for new observations that are accurate if you are overfit on the training data. And so the test data helps prevent this. Now, a few notes that are important about the test data, things that I have seen go wrong as a referee of papers or when working with students that are doing machine learning for the first time. And that is that the test data, if it is truly your test data, should never, ever be looked at, examined, peeked, anything until you are done. You are certain that you are done making changes to your machine learning model. If you examine how a model performs on the test data and then you adjust the model after that point, this is what's called snooping, okay? And it essentially negates the purpose of having a test set in the first place, right? So I just want to make this very clear because this is not what we did during Notebook 1. During Notebook 1, we were just training on all of the labeled data and then looking at how well the model performed there, right? That's often what's referred to as the training error, but the training error essentially tells you nothing about how well your model will work once you start applying real data, unlabeled data into your system, okay? And so that's the last portion of this diagram here at the bottom. Once we've gone through this hard process of training the model, we want to take the unlabeled data, pass it through the machine, and get predictions for either classes or our regression target for the new sources. Okay? In almost all instances within the workflow of building machine learning, that last step is more or less instantaneous. So it's the training, all right, and understanding how do we optimize the model itself that takes most of the user's time. Okay, so I want to talk a little bit now about training sets, which I've mentioned previously are very difficult to build in astronomy, right? I said this before, I'm going to repeat it now. The single most important thing worthy of your attention as you start to think about how to build machine learning models is your training set. Okay? The algorithm can only learn what is in the training set. So it's very, very, very much the case that garbage in equals garbage out, right? There's very few applications where that could be more true than a machine learning model. If you have biased data, if you have data that doesn't properly reflect the sample that you ultimately are trying to classify, you're not going to get particularly useful classifications at the end of the day. Okay. So I mentioned sample selection bias earlier, but here's sort of a graphical representation of what I meant by that. And this is not perfectly accurate. This is more just to be illustrative. But for the very famous Sloan Digital Sky Survey, there was both a spectroscopic and a photometric component of the survey. And here I'm showing basically the distribution of sources that have spectroscopic observations. Spectroscopy is often used for labels in astronomy, and the distribution of sources that have photometric observations, right? And there's several things that you may notice, right? The peak of these distributions is different, and the amplitude is particularly different between these two. So this brings us to the first breakout question of this afternoon's lecture, okay? Given the distribution of SDSS sources with spectra, how would you build a training set if you wanted to classify everything that is in SDSS? Okay. And I'm going to pause now. I'd like for you to just take a couple minutes to discuss this with your partner. And I'll flash back to the figure in just a second so that you can look at that as you discuss. But we're going to break for 2 or 3 minutes now. Okay. So I think Brian is going to help facilitate, but I'm just curious for any thoughts in the room. How would you work to build a training set given the limitations shown here?
We can start it off, I guess. So I guess we were a little confused at first. I guess if you knew sort of the width and the mode of the SDSS photometric histogram or sample, one thing you could do, you could just try to generate synthetic data. That would probably have its own, systematic biases, but just try to generate some synthetic data to include in your training set so that you don't overfit to just the spectroscopic sources.
Okay, yeah, so we could try to develop some simulations or synthetic observations in order to supplement the spectroscopic observations to better match what is observed photometrically. And I agree with the point that you made, Joey. I mean, you have to be careful as you're building simulated data because it is often the case that we don't perfectly understand the way these systems work, but that could work, yeah.
So we were talking about that there are faint, far objects in the photometric data set that are not all represented in the spectroscopic one. So
Uh-huh.
you can't possibly make a model that would, be representative of the entire data set that you have.
Okay, so Amir and group think we should just give up. No, I'm kidding. You're absolutely correct. The faint sources in this case cannot be potentially perfectly modeled by the bright sources that we have. That's correct. Yeah. Any other ideas?
I mean, if we were just brainstorming, I guess I could say something stupid. I was thinking, why don't we just maybe look for more dimensions and see if there's a cluster that has a bunch of spectroscopically classified things, and just like a little percentage of like non-classified things, and then we just assume that those belong to the same class, and then you just have a larger training set.
Okay. So that sounds like what we mentioned at the end of last lecture, to do something like a semi-supervised method. So use all of the data, try to find clustering within all of the data. And then if you have a cluster with many classified examples, take the other examples within that cluster and assign them to that class in order to expand your potential training set. Yeah, look, these are all great ideas. And the truth is, I don't even have an answer in the slides for you right now. But this is basically, this is the kind of thing that I think you need to be thinking about. A couple other things to consider, or avenues of pursuit. You can look for representations of the data that don't hinge upon individual brightness measurements. Okay, which is hard. But if you don't include R magnitude as a feature, and you can instead find some way that can compare something that's at 18th mag and 21st mag, then that may be a way to build out your model. Okay. So there's a lot of different approaches that you can potentially consider. And these are all great ideas that you had. Okay. All right. So in order to build a training set, you need labels, all right? And in astronomy, we have a few different ways to get labels. The sort of standard in the machine learning literature is to establish ground truth. And I am jokingly saying that this is actually impossible in astronomy, right? We cannot actually physically travel to a star and say, oh yes, you are clearly a K star. Thank you very much. Good to meet you. Good day. Right? Unlike, say, if you're doing an experiment where you're trying to figure out whether or not a car sells, for some subset of data that a car has sold, right? So instead, we use several proxies and then often call these things ground truth. Spectroscopy is probably, in many instances, the holy grail. So if we are able to make a spectroscopic measurement, we can typically say with a great deal of confidence, this is a galaxy, or this is a star of this particular type. Of course, spectroscopy itself has noise and sometimes can also be difficult to classify. So that can lead to things like noisy labels, right? The challenge with spectroscopy is that it is expensive. It costs a lot of money to build a spectroscopic instrument, and it's limited to relatively bright sources, as we just saw. Another way to get labels is via expert annotation. So we all, as much as painful as this is, we should probably all at some point in our careers actually sit down and have to look at like 1,000 images. And I contend this is actually a really good way to build expertise, but this is also expensive, right? This is expensive in terms of the time that's necessary. There's probably a few experts in the world that are better at looking at and determining whether a galaxy is an elliptical or lenticular or spiral or whatever. But getting those people to sit down and do that for 1 billion sources is really, really challenging. Furthermore, experts hate looking at true negatives, right? So if I'm going to look at a whole bunch of data, I want to find the thing that I want to find, and I'm going to do whatever I can to avoid looking at true negatives. But if I'm going to build a model, right, I need to have lots of examples of true negatives. Okay? Another way to get labels is by cross-matching to reliable catalogs. So someone else has built a model, and I mostly trust that model to tell us where all of the low mass galaxies are. So I can cross-match to that model. But challenges there are we don't know the error rate for the other catalog, and we also don't know the error rate in the cross-match algorithm, which may also have problems. And then finally, gaining popularity, especially of late, is different ways to do crowdsourcing for label annotation. So this is something like the Zooniverse or the very famous Galaxy Zoo project. If you haven't heard of it, maybe someone can quickly drop the Galaxy Zoo link into the Slack. The challenge here is that we are relying on non-experts. So the hope is that if you get many votes from a non-expert, that you will still get a correct classification, okay? So there's a lot of ways to get labels, but none of these are particularly easy, unfortunately, okay? Because the best ways are expensive. They either take a lot of money to build big spectrographs or a lot of your time, and they can also be biased, right? If experts are not going to look at true negatives, then you're going to probably have a biased subset that you have classified. Okay, so before we get bogged down in algorithms, which is what we're going to get into next, and the details of how you build a machine learning pipeline, I just want to take a moment to tell all of you to please worry about the data. And indeed, this is like the theme of the DSFP, worry about the data. All right, so moving on. Just as we did in the unsupervised lecture, there are way too many methods and algorithms to conduct supervised learning for me to go over all of them, or even to come anywhere close to going over all of them. So instead today, I'm just going to focus on 2 methods, again, to help develop intuition, and we'll cover more methods as we go throughout the week. But this literature is really vast, so we can't cover it in the time we have. Okay. First and foremost, let's start with the KNearest Neighbors algorithm. So the algorithm itself is simple. The pseudocode looks like this. We're going to specify a number k. That may sound familiar. It's very similar to k-means. We then want to identify the k closest neighbors, okay, to any source that we are hoping to classify. All right. Then the plurality of those neighbors determines the classification of our new source, okay? So the k closest neighbors in the training set are used to classify the new source, right? This is, I think, a bit easier to see if we show an actual plot. So here's a data set with sources from 2 different classes in a 2-dimensional space, okay? We can see that the lower region here is mostly the purple class, and the upper region here is mostly the orange class. The shaded background is the results that you would get from a k equals 3 nearest neighbors classification algorithm, right? And so you can see, right, there's like a small island here that is the purple class because there's 2 purple sources that are close to each other. So as long as you're in this vicinity, whatever the third source is will be outnumbered if you were to vote. Showing the results of the same data set, but a k equals 15 predictor, right? We find fairly similar results, but a smoother boundary in this case, right? Because we need far larger number of neighbors. So at any point in this 2-dimensional space, and here we have a zoom in on the boundary on the relevant area, right? Wherever you are making a prediction, okay, you just find the 15 nearest neighbors and you let them vote, essentially. And that is how you assign the classification, right? So much like k-means as a great starting place, k-nearest neighbors is a really good starting place for supervised learning methods, okay? Of great power, a few decades ago was the introduction of decision trees, which can be used for both classification and regression. In a decision tree, the training set is recursively split based on tests of the individual features. So, you know, you have all your sources here, at the very top of your tree. And then we say, okay, we're going to split on a value of width equal to 4. So everything with a width greater than 4 goes over here in our tree. Everything with a width less than 4 goes over here, right? And then we keep splitting, right, recursively until you reach some pre-specified stacking criteria. Any new source that you have can then be propagated through the decision tree in order to assign a final classification. Again, here's a quick image to illustrate how this works. So on the left here is a 2-dimensional feature space, X1 and X2. And there are 5 classes in this 2-dimensional space, R1, R2, R3, R4, and R5. So at the very top of the tree, we're going to split on a value of X1 equal to S1. So here's our splitting point, okay? And as we look at things less than S1, that means we're moving all of the R1 and R2 sources on this side of the branch of the tree. And we're moving all of the R3, R4, and R5 sources on this branch of the tree. Okay. We can then further split the data. Over here, we're going to split on S2, X2 value of S2, which allows us to separate R1 and R2. While over here, we're going to split on X1 equal to S3, which allows us to isolate the R3 class, while one more split is necessary on X2 equal to S4 in order to separate R4 and R5. Decision trees are actually extremely powerful. This is a pretty simple method, but these methods work really well when it comes to classification problems. The problem with individual decision trees is that they can give you very high variance results. So depending on what branch a source is propagated on at the very top levels of the tree, will have a very significant outcome on the final classification that is assigned. Okay. It was realized in the late 80s that using multiple decision trees could actually mitigate some of those problems. Okay. And one of the most popular methods along these lines is what's known as the random forest. Right? So a random forest, it's called a forest because there are multiple decision trees. Furthermore, there are degrees of randomness that are introduced, which actually improve the ability of the model to classify unobserved sources. So one thing that's done in a random forest is the use of bagging. So every individual tree in the forest is actually trained by a bootstrap with replacement sample from the training set. Okay. Furthermore, for every split within the individual trees, only a random subset of features is considered for the splitting criterion. And the reason this is done is to decorrelate the different trees, right? Otherwise, you would have a structure in every tree that's very, very similar. And then finally, the average of the decorrelated trees is used to make a final vote on the classification of any new source. And it's clearly been shown that random forest and other sort of similar multi-tree methods reduce the variance versus a single decision tree. Okay. So graphically, this looks something like this, right? You have some source or feature vectors X, you pass those feature vectors to some large number of trees, okay? And then all of those trees are aggregated at the end in order to make your final prediction or your label Y. Okay. Finally, for completeness, I just want to quickly mention the sort of best method, still best method to this date, if one is not using deep neural networks, is known as boosting. Boosting is also using many weak learners, essentially a bunch of small decision trees. But the idea is that as part of the training, sources that are misclassified during training are reassigned more weight. So a decision tree is made, but then the decision tree is updated. Essentially, the weights are updated so that misclassification, the probability of misclassification goes down. The state of the art from the first lecture that I gave today, where we were looking at how well images could be classified, the state of the art before deep learning was all people using this boosting method. And there's now a famous library called XGBoost. It's linked here in the notes. But if you want to build a model that is not deep learning related, XGBoost for almost all applications is going to be your best solution in that regard. All right, so This is all that I just said about boosting, excuse me. Okay, so I want to end today just by going through the process of building an actual machine learning pipeline. And these steps are algorithm independent, essentially, but this is how you would go about actually, building some pipeline that is then going to show up in a paper that you write, right? So here we have basically the building blocks for your machine learning pipeline. You start with some historical data that goes into your modeling process, where you're going to build a model that's essentially relying on the algorithm you choose. You want to then evaluate your model and optimize it appropriately before eventually making predictions on new data. Now, in some instances, as you make these predictions, you can then get follow-up. You can actually get the correct answers, and that information can be fed back into the machine learning model as additional sources for training. So in astronomy, this is like, let's go find a whole bunch of extremely massive galaxies. We then go take spectra of our candidates, and we can feed those spectra back into the model in order to refine how well it works, right? Okay, so before we can get started, we have to prepare all of the data. So this means we're going to query some database if we're using something like the Sloan Digital Sky Survey, or we're going to go collect new observations if we're the Rubin Observatory and we have no data, or maybe even build simulations, right? We might be trying to build a model that can make predictions based on some simulations, right? So we want to collect all the data to be modeled. At this stage, it's a good idea to worry about the data. All right. After this, we want to select features that we're going to use in the model. We then want to determine the ground truth or the labels for the training set. Okay, so we have the data, features, ground truth. All right. We may need to convert categorical features within our data set. So what do I mean by that? Our machine learning models don't have to be limited to things like, here is a measurement of mass, right? We can also include things like a categorical feature. So here's an example, color, right? So maybe we have a whole bunch of galaxies. Those galaxies are red and purple. Well, numerically, we can't just pass red, purple into something like a KNearest Neighbors. But what we can do is create categorical features, right? So we could have red be a series of ones and zeros for things that are red. Purples be 0 and 1, right? So this is one way that we can take categorical information and make it work in numerical models, right? Then we need to look at things like missing data. And this came up in the second breakout problem from this morning's lecture. But if there is missing data within our data set, it's important to either impute it, so try to come up with some estimate for what the missing values are, or if a very small amount of data is missing, it may even make sense to remove those sources entirely from the training set, okay? So what sort of strategies should we use if there's missing data? And missing data comes up in Astro all the time. If you go to the Sloan database, you go to the Pan-STARRS database, you eventually go to the Rubin database and you say, I want the photometry of everything, right? There's going to be all kinds of sources that are only detected in the R band and the I band, or they're only detected in the Z band and the Y band, right? There's going to be other measurements that are not available. There's going to be fluxes that haven't been measured. And there's a variety of reasons why this could happen. And here's some strategies for what to do when this occurs, right? So if the missing data has meaning, so is the magnitude measurement missing because the source is too faint, okay? If the answer is yes, then you should replace the missing value with some numerical value, or alternatively, you can create an entirely new categorical variable that says missing too faint, right? And then binaries, ones and zeros, right? If the missing data doesn't have meaning, okay, then there's a few different things you can do. If you have a very large data set and only a very small number of values are missing, like I said, I would just chuck the sources that have the missing data, right? If you have a large data set and everything is temporal, right? So you have a time series and your missing observations are like, oh, for whatever reason, the instrument didn't measure the flux at time t100. You can just replace those values with the previous value, or you can do a simple interpolation from t99 to t101. if you have some simple distribution in the data set, right? So if you have missing data for a feature that very clearly is normally distributed, you can just replace the missing value with the mean or the median, and that essentially will have very little diagnostic value as you're running your machine learning algorithm. Or finally, in some instances, you can build an entire separate machine learning model to predict the values of the missing data in order to fill in those missing values. Okay? And that is these last steps, when you're replacing missing values, that's all called data imputation, essentially. Okay. All right. After that, it's typically a good idea to normalize the features. This has come up a couple times today. I will quickly add that one thing that's really nice about decision trees is that the features do not in any way need to be normalized, because you're just looking for some point in the middle of the distribution of a feature to split the data, okay? But for something like K-nearest neighbors, if you have a very, very wide distribution in one feature and a narrow distribution in another feature, the wide distribution is totally going to dominate what is and is not considered to be a neighbor. So this is why you may want to do a normalization, okay? And then it's always a good idea, always a good idea to visualize your data set, to spend at least a little bit of time looking at what it is that you have measured or what it is that you are attempting to measure. And the reason for this is that it may be that you have something that's totally garbage, or you can find some systematic very quickly without having spent a lot of time building a machine learning model and finding out that the results themselves are somewhat meaningless, okay? So at this stage, after you've prepared the data, I think that it would be a good idea for you to worry about the data. Always worry about the data, please. Okay. All right, so after you've prepared all the data, you may find that it's necessary to undergo some feature engineering. And we'll talk about this in more detail tomorrow. But the basic idea behind feature engineering is that the features that you have may be insufficient, right? So maybe you query the SDSS database and you find that the features you get there are not sufficient in order to separate your spiral and your elliptical galaxies, okay? So part of the feature engineering process can be adding new features. That can be as simple as, oh, it turns out that if I take my G magnitude and I subtract that from my R magnitude, I have this new measurement called the G minus R, and G minus R is really useful for classification, okay? So that's an example of feature engineering. You can also come up with stuff that's entirely new, like I need to go to every galaxy and observe it in some new way so that I have a new measurement, okay? Feature engineering also involves the removal of noisy or uninformative features, okay? So it turns out that if you take the timestamp of every galaxy measurement in the SDSS database, that's not going to be very useful in terms of being able to classify whether or not you've found an elliptical or a spiral galaxy. So the next step, after you've prepared all the data, is to work through model selection. Essentially, this just means picking an algorithm. Here's just a flash up from scikit-learn for 3 different data sets, 1 in each column here, how 5 different models, some of which we've discussed, some of which we will discuss, how they actually divide this 2-dimensional space to classify these different sources, right? And you can see that actually these different algorithms provide fairly different predictions depending on the model that's being applied, okay? So you want to pick an algorithm. Well, Adam, what if I have no idea? I have no idea what algorithm. If you have no idea what algorithm, honestly, I would just like pick 3 and go with the one that works the best, okay? Typically, nearest neighbors, if you're doing simple supervised classification, is a good one to be one of those 3 because it is sort of so simple in the way that it's implemented. Okay. All right. Critically, after you have selected an algorithm, or perhaps even as part of your algorithm selection process, you want to evaluate your model, right? And we've talked about this briefly, but it's very important to avoid underfitting and overfitting, right? So here we have just a simple cartoon, some data that seem to follow a quadratic relationship. but there's some noise in the observations. On the left, we have a dramatically underfit model, right? This is a highly biased model. Essentially, it doesn't matter what your input is, the output is always the same. On the right, we have a severely overfit model, right? So there are wiggles in the data. Those wiggles are essentially noise, but on the right, we're fitting that noise. And so that means we have a high variance model that's not going to generalize well if we make some new observation, okay? This game of optimizing your model and evaluating it is essentially a way to try and find the optimal trade-off between bias and variance. So here we have some examples of low variance and high variance. In the upper left-hand corner, right, high bias, low variance, that is an underfit model, right? So it doesn't matter what the input is, you're always going to get roughly the same output, okay? In the lower right-hand corner is a low bias but high variance model. That's an overfit model, okay? So small changes in your input features are going to lead to very wildly different predictions, okay? Ideally, we want low bias and low variance. And typically, as you adjust tuning knobs within the algorithm, you're basically balancing the variance and the bias, all right? Okay, so how do we do this? I think the best way to do this is to use cross-validation. So the idea behind cross-validation is that within your training set, you can basically test how well you are training your model on the training set itself. The most popular form of cross-validation is what is called k-fold cross-validation. So you take your training set, you divide it into k equal partitions, as shown here. You then remove one of those partitions, we'll call that fold I, and you train the model on everything else within the training set. You then make predictions on the sources that were withheld from the model, okay? And those predictions can then be compared to the correct answer. So this is somewhat similar to having a test set, except it's all sort of done internally with your training set. And so you can make different changes either to your algorithm or to the tuning parameters of your algorithm. You can, if you iterate over all of your k folds, you can get a prediction for every single source in your training set, but the predictions come without having used the source in training itself. And you can compare the two to see how accurate your classifications are, or you can look at how precise your, precise is not the right word. You can look at how accurate your regression metric is as well, okay? So cross-validation is the way that we basically tune up our model while working just with the training set, okay? We discussed some metrics this morning, like looking at true positives and false positives, okay? Using this nomenclature, using true positives, false positives, true negatives, and false negatives, we can develop what's called the confusion matrix. For a binary classification problem, a confusion matrix is not particularly insightful, but if we have a multi-class problem, the confusion matrix can actually be incredibly useful, right? So here's an example of on the order of 30 class classification problem, and the confusion matrix here is showing the predicted class as a function of the true class based on cross-validation for everything within the training set for this data set. And you don't need to understand what the different rows and columns are here. What you need to know is that ideally, all of the power would be along the diagonal of this figure, right? So we want to be predicting the true class in every case. And then all of the off diagonal power indicates classes that are consistently being misclassified, right? So over here, we can see that all of this class V is actually being misclassified as class F, right? And so that tells us that if we want to go back and work on our feature engineering, we should be working on or thinking about how can we do a better job of separating instances of class B and class F. So the confusion matrix is really useful in that regard, okay? Other things we can look at are the true positive rate and the false positive rate. So the true positive rate is just the number of true positives divided by the number of true positives plus false negatives. Okay, the false positive rate is the number of false positives divided by the number of false positives plus true negatives. For many classification models, there's actually what is known as a decision threshold to determine whether or not a source belongs to the positive class. And if you adjust that decision threshold, you change both the true positive rate and the false positive rate. And doing that in concert creates what's known as an ROC curve, or receiver operating characteristic curve. So these are very common way to look at how well a classification model works, okay? So ideally, what you want is a true positive rate that is very close to 1. Essentially, you can find all members of the positive class without misclassifying them. And if you do that with a false positive rate that is also close to 0, meaning that you have very, very few false positives, you've built an excellent model, right? So here we show several characteristic ROC curves, and this orange curve here is the one that's the best, because this is the one that gets closest to the optimal position of true positive rate 1, false positive rate equal to 0. Okay, and we'll build some of these in the notebook in just a moment. Okay, I would also argue that critically for astronomy, a lot of our problems are highly imbalanced. So if you're building a machine learning model to go find some rare subclass, right? I want to find all of the extremely metal poor stars. I want to find all of the ULERG galaxies. Okay, when you're looking for a class that is very, very much in the minority, the precision is also a good metric to look at. So this is the number of true positives divided by the number of true positives plus false positives. So why is the precision useful? Suppose you're looking for these rare things, right? You can build a model that has pretty good accuracy. You could even build a model that has a pretty good true positive rate. But if that true positive rate correspondingly comes with a whole bunch of false positives, as you go and try to obtain follow-up, you're going to mostly be looking at things that are not part of the class that you care about, right? So recall is the same as true positive rate. Precision recall curves are often used when you have sort of high value follow-up targets in a minority class, right? So ideally, you would have a precision and recall that are both equal to 1. You want to find only the positive class, and you want to do it with sort of perfect purity. But it's often the case that precision recall curves sort of fall like this, where you're looking at a trade-off between the number of false positives you get in order to maximize the number of true positives that you recover, right? Okay. And then finally, it's important as you evaluate your model, as you pick your algorithm, to optimize the tuning parameters for your model. So every machine learning model has tuning parameters. There are defaults for everything within scikit-learn, and we will typically be using defaults as we work in our notebooks. But in practice, you can get better performance as you change these parameters. So here's an example showing 2 parameters for what is known as a support vector machines model. And you can see that this particular model in this particular example, right, the accuracy is shown here on the right with darker colors being more accurate, is not particularly sensitive to the penalty parameter C, right? Results are somewhat constant along that direction, but the kernel coefficient gamma, small values of gamma, give significantly better classification results than larger values of gamma, okay? How do you test this? Again, that's done in cross-validation, okay? So to optimize the model, we just try a whole bunch of different parameters. Typically, this is done through brute force, through a grid search, and you just evaluate with cross-validation what are the parameters that give the best performance, okay? And then after you've done all that, finally, you get the reward. You get to take the new sources that you have observed, pass them through your model, and make predictions on what it is that you have found, okay? So, and this, if you haven't already, is when you truly need to be worried about the data, okay? Because it is this last step that is the critical one, the one you've been building towards. And if you have any problems in your training set, those are going to show up in the final predictions that you make. During one of the breaks, if you want, you can ask me about spectroscopic resources that were used to follow up very poor candidates because I was not sufficiently worried about the data, okay? So again, we have our historical data, we go through the model building process. We pick an algorithm, we pick multiple algorithms. We evaluate those algorithms using cross-validation. We then optimize the algorithm of choice, again, using cross-validation, before we essentially say, now our model is done. At this point, we then apply the model to our test set, and we get some estimate for how well the model is going to work for unclassified sources. And that is when we finally get to make predictions at the very end of our machine learning pipeline, okay? Notice, again, in this last portion of the talk, I did not once ever say, this is the algorithm, right? This process, if you're doing machine learning, even if you're doing deep learning, this process is the same, right? Okay, so in conclusion, supervised methods are very useful for classification and regression problems. Okay? Cross-validation, as you're tuning up or choosing your algorithm for the model, really is important in terms of preventing overfitting. Okay? It doesn't matter what algorithm you want to use, the process for building a machine learning pipeline is exactly what I laid out in the second half of this lecture. And I know you're sick of me saying this, but this is the DSFP mantra. So please get used to it. You will hear it again and again and again. But please, please, please worry about the data, right? I spend all my time fretting about the data that's going in. I spend a very little time worried about whatever algorithm I've chosen or how I'm going to construct the architecture, right? Those things, relatively speaking, can be done quickly as long as you have a good training set. So that's my big takeaway, not just from this lecture, but I think for the entire week. Please be worried about the data. Think very hard about your training set and potential biases that may be present there. And with that, I'm done, and I'll be happy to take your questions. Thank you.